Okay, today we're going to talk about a different approach to modeling. It's called semi-Lagrangian method. So all fluid dynamics equations that we considered so far, that we employ in our field, can be written in two ways. First one is so-called Lagrangian view, when you have, say, some quantity phi. It can be scalar, it can be a velocity, you name it. Is that this material derivative of total derivative in time of some quantity phi equals to some sink and sources of phi. So those are sinks, sources. And this is a Lagrangian view of the fluid. Or it's basically trajectory. So this is rate of change of some quantity phi following a trajectory in the fluid. So some trajectory here. So you're sitting on a, say, boat, and you carried by a river with a current, and assuming that boat doesn't have any inertia, it would follow the streamline of a fluid. This is what Lagrangian derivative implies. This is what this equation implies. So it's a following follow a parcel method. And there is another view, which is called Eulerian view, which basically you can write this full-time derivative in terms of partial derivatives in time and space. So this d phi dt equals to d dt phi, partial in time. So, and partial derivatives imply that other variables are frozen when you take derivative in certain in that variable t or in space, plus u d phi dx plus v d phi dy plus w d phi dz equals this q. So this is Eulerian way, or Eulerian view. So it's a view at fixed point in space. So instead of following a flow in Lagrangian view, you're actually sitting at some point here, fixed point, and observe how this quantity phi changes in time. And you also observe, maybe you can compute derivative of this phi in space in that point. So you're not moving anywhere. And so this is, those views are of course equivalent, mathematically equivalent. But of course in practice, when you apply it to solving the equation, they are quite different. So Eulerian view is more compatible with a fixed grid. So you have grid, and grid, assuming that grid doesn't move anywhere, just standing there. This is what Eulerian view of the world is, that we use in our numerical method. So far we've been using this Eulerian approach. And for Lagrangian approach, but you can use Lagrangian approach or a Lagrangian view to apply to, instead of solving this, for this, you just solve for this. And what's the advantage of that? Well, first of all, remember our stability criteria, which we derived for stability criteria for finite difference schemes that we used before, or finite volume schemes, regardless. Actually, use all these derivatives in space, like Courant number. It's based on grid spacing and time spacing and so on. So the Eulerian view creates stability problem for the schemes because we use this discrete grid. Another thing that Eulerian view, another problem that Eulerian view has, is that it has all these nonlinear terms when you multiply variables. Remember that this is what creates nonlinear instability issues and other issues like aliasing on a grid that I considered before. So in Lagrangian view, there are no nonlinear terms, like it's just quantity phi following a trajectory. And in Eulerian, so we don't have all these Eulerian nonlinear terms. So that also kind of would be nice to. That's a nice property of Lagrangian view. So in Lagrangian, so we could use this Lagrangian view to actually avoid computing all this, and for that we could just solve this equation directly, numerically, and basically, generally we would look for some solution like phi at time step n+1. At some point x n+1, but this one is not grid. I'm not writing index here for grid. Just at some trajectory n+1, and say let's consider like two-dimensional, one-dimensional case equals to phi n at point xn. So a plus integral of this right-hand side q from time tn to tn+1. You have this q as a function of x and time integrated over time. So basically we just integrated this equation directly. So if there is no q, then it just along the trajectory those two values are the same. So this is called arrival point, and this is departure point. So we have some, let's say, this is your departure point, and this is arrival point. This is departure point. So along that trajectory, solution is very simple. You just compute your arrival point using departure point and velocity field by using the fact just that u equals to definition is dx dt. It's kinematic kind of relationship, just rate of change of x coordinate in time. So you can compute your x n+1 equals to xn plus integral from tn to tn+1 of your u, the function of x and t, dt. So in one dimension, in two dimensions it would be like y equals to yn and so on. In three dimensions it can be z and so on. So you assume that you have this velocity field somehow, you specify it, or it's on your grid, so you interpolate this velocity points and then integrate, and that's not easy actually to do. So because you cannot just, you see this u is on your grid as a function of x, and you need to integrate it as a function of time. So it's some additional interpolation, some additional scheme should be used to compute this arrival points. So, but this is basically the method. Basically the whole Lagrangian method is how to find, like in this case would be how to find arrival point. And as long as you found the arrival point, you just start all over again. Your arrival point becomes departure point, and then you keep integrating in time. The problem with this so-called Lagrangian method, so this one is Lagrangian method. So in Lagrangian method, you find arrival point given departure point. So this is called Lagrangian method. So the problem with Lagrangian method that imagine that initially you have some regular departure points and then some velocity field, and then you find your solution, and it may be like that. So your nice regular arrival points, after a while becomes kind of your your regular departure points. After a while your arrival points will be all over the place, and if you keep going like that, very soon you may have some places where there are many points that you follow, and then some places where there are no points. You can of course launch new departure points, but then it's going to be total complete mess. Total mess. So this is not very practical approach, especially in maybe in one dimensions, and this method is actually used in one dimension, say for compute microphysical processes in clouds, like one dimension in say cloud droplet space, so size cloud droplet radius space, for example. We could in principle use that method. You grow your radius, you kind of evaporate it, and so on. So it's you're moving back and forth, and it has been used for so-called partial models of microphysics. But in a three-dimensional, two-dimensional actual compute modeling of, say, of cloud processes, advection and so on, diffusion, this method is not very practical in Lagrangian because of this problem that your points will be all over the place. It's difficult to interpolate to do anything. And also, you may concentrate in certain places and create these bold spots in other places. So this Lagrangian method is basically never used in three-dimensional or two-dimensional modeling. So what can you use? Well, instead of finding arrival point, why don't you actually use arrival point and find departure point for that point? What's the advantage? Well, then you can actually basically use your arrival points are the points on your regular grid. And then you will find departure point by reversing time. So this is your at time n+1, you know where you should arrive. Your Lagrangian trajectory should arrive. But you basically now need to find points where actually they started from. So you look for departure points. And then you find values there on your regular grid by interpolation from neighboring values of that field that you like phi is defined on this grid. You interpolate, and then you basically you know your arrival point, which is still on this grid. So basically, this is what you need to do to find a departure point for your arrival point that you know. And in that case, so on each time step, new time step, your arrival points are the same. So there is no danger that they're going to concentrate in some places or create some bold spots in some other places. And each time you just basically compute new departure points. So that's in essence a so-called, this is in essence what's called semi-Lagrangian method. So semi-Lagrangian method is a look for departure point given arrival points on a grid. So that's much more practical and much nicer problem. So this is what semi-Lagrangian method is. So let's consider an example. So basically in semi-Lagrangian you reverse time. Because your arrival point, and so you need to find departure point, so you need to reverse time, reverse your basically velocity field, and go backwards and see from which point information to this grid position actually arrived from. So let's consider example, one-dimensional example of semi-Lagrangian approach. So 1D, let's consider 1D advection. So 1D advection problem that we always consider. It's we're solving this equation d phi dt equals to minus c d phi dx. This is the example we always use. This advection with constant velocity c, which is greater than 0, and also c is constant. So let's consider this simple example first. So basically, as we did in one of the previous lectures when we considered advection schemes, simple advection schemes like upstream bias scheme and so on, let's use this diagram. So we have time in this axis, space in this axis. So we have our regular grid. Let's say that grid spacing is constant. So this is time step n plus 1, and this is time n. So we know our arrival point. Let's say this point. It's with index k. Here's k minus 1, k minus 2, and so on. This is some say k minus 3 and so on. So this is our arrival point, and we need to find departure point. So we know that signals propagate with velocity c. So there are so-called characteristics, or in this case one characteristic. Characteristics is basically trajectory in space-time. So it's line in this case because c is constant. So let's say that it's actually, if we trace it back, it should be line, straight line. If we trace it back, this is arrival point, so this is departure point. I mean, this is arrival point, sorry. And we know that coordinate of that arrival point is just our grid point. And this is departure point. And it's somewhere in between some indices. In this case, I've drawn it between index k minus 3 and k minus 2. But it can be some other point, depending on your time steps. Here's delta t. It can be larger time step, smaller. But in this case, we can easily compute where this point is, given delta t. And then we just interpolate to find this value here. We just interpolate between two given points. And then this value equals to the value in here, because it just advected to this grid point. So this value in this point now equals just to value, interpolated value in this departure point. So let's call this one as x star location. This x star location equals to xk minus c. You see we reversed time, so our x is actually going now backwards. assuming that c is constant here, positive here, minus c delta t. So now how to find indices where it would go? Well, the whole length, this delta t, delta x, this x distance, you see that xk minus x star, this distance that it partially traveled, equals to c delta t. So in order to find this, let's say this delta here, this delta equals to this xk, or this c delta t, minus this I delta x, where I is just integer number which equals to index to this, like this index is actually like k minus 1 minus I. So this I can be computed as I equals to some int of c delta t divided by delta x. You can actually see that. Int meaning converting this integer, this real number divided by delta x. It can be some real number with fraction in it. Int converts it to integer number, so basically throws away. Like for example, int of 3.6 equals to 3. Int of 3.1 equals still 3. So it's not rounding up to nearest integer number. It's just making it integer by throwing everything after the point. So you can see this. So then, if you know I, you compute your delta, and then if you know delta, you can interpolate using this simple linear interpolation that we considered before. Then your phi k n plus 1 equals to value in this, like this value equals to value this point. So you just use interpolation. It's basically delta divided by delta x phi k minus I minus 1 times step n, and plus delta x, this whole distance minus delta divided by delta x phi k minus I n. I believe I did it right. No, it actually should be, this point is k minus 1 minus I, and this one is just k minus I. Yeah, that's more like it. So that's basically the scheme. So basically, and because you always interpolate, it means that the scheme is going to be stable. Remember that instability actually arises when you extrapolate values. When you interpolate, it's usually a stable scheme in this case. So this scheme kind of, so you can substitute delta in here and get the full scheme. So this is semi-Lagrangian scheme for this problem. Now, let's assume that this distance that it travels, the signal travels, does not exceed delta x. So it's relatively small delta t. So in that case, so let delta t be such that, like for this, that I equals to 0. So C delta t is smaller than delta x, so it's going to be like the number, say 0.2. Then int is going to be 0. So in that case, actually, if you do this exercise, you substitute in there, you will get the scheme phi k n plus 1 equals to phi k n minus c delta t divided by delta x, phi k n minus phi k minus 1 n. And you would immediately recognize this one is upstream by a scheme. That we used before. It's first order in space and time. So you see that semi-Lagrangian method, for the case when stability criterion is satisfied, is just basic finite difference scheme. So there is no advantage of using semi-Lagrangian method if your time step is small enough. The semi-Lagrangian method shines when your time step is much larger, let's say, than your time step larger than required by stability criterion for Eulerian grid. So this stability criterion is for Eulerian grid because you need to be interpolating. But semi-Lagrangian only makes sense and gives you advantage when you can run it current numbers are larger than, say, 1 that required by this scheme. Say current number of 3 or 4. Maybe not very great current number, because it becomes kind of too much error would be generated, because you basically assume the way how you compute this departure point, you assume, like in this case, it of course can be any delta t because c is constant, but in reality c is not constant, it's some velocity and it's actually changing. So making it too large current number would produce some errors, truncation errors. But probably for current numbers 2, 3, 4, it's okay. So it's just 2, 3 grid points. So then your semi-Lagrangian method would shine. And because semi-Lagrangian method can be more expensive per time step than Eulerian method, because you involve interpolation, especially in 2 or 3 dimensions. But you compensate that by allowing larger time steps. And that basically you have advantage over Eulerian grid. So semi-Lagrangian only has an advantage over Eulerian grids when you have large time steps. So especially semi-Lagrangian method is very nice in places where there is very high resolution, so that your grid spacing is very small. Let's say on latitude longitude grid on sphere, it's in this near pole region. So remember, in order to run using Eulerian method, we have to use something like a polar filter. But in this case, you don't need any filter. You just basically can run at much higher current number by basically computing trajectories near the poles and then interpolating, like just using interpolation, and it would be completely stable. Would be nice. Like you can run at current, say 5 or 10 near the pole, and it would be stable. Of course, some care should be taken that how you actually do that around the poles. So it's a little bit specific topic. I'm not going to talk about that in detail. So how you actually, so what about some case when c is not constant, so it's actual velocity? How you find your departure point? So that's actually the all differences between among different semi-Lagrangian methods is basically that's how you find this departure point and what kind of interpolation you use. Obviously, first order interpolation is not very accurate that we used here, for example, or you need higher order interpolation. For example, like in 2D, if you have problems like this, the phi dt plus u phi dx plus w d phi dy equals some q of xy. So in this problem, two-dimensional, you have now variable u and v, and you need to find your departure points. So you need to find departure points, which you can do using, like for example here, just first order scheme like that, that your departure point equals to your x coordinate on a grid point ij, and n plus 1, well, we assume that it's, of course, x itself, let's say grid does not move, so just your coordinate minus u, your velocity field in the grid point ij, and you take it at, say, time n plus 1 half. So you assume that your velocity field is known at n plus 1 time step, and it's known at time step n. So you just compute basically average of them. So that's more accurate. So it's kind of like semi-implicit scheme here. And times, and you make it like delta t over 2, let's say. So you just move half time step. So this is your provisional point. Let's call it double star. So you could just use that as a whole scheme, but that would be only first order accurate in time. But if you want second order accurate in time, you do it. So this one kind of predictor step, and then you do x star equals to xij minus, now this u, you computed this double star point. You find it by interpolating. You computed in that point at halfway through, so delta t over 2, n plus 1 half, times delta t. This time you take the whole time. So this scheme is second order. It's O delta t squared. This one is O delta t. Well, if you use the whole delta t, of course, here. But I mean, this scheme would be second order in time. You can use other approaches. For example, you actually have, if you have time tendency of u from your model computes tendency, right? It's kind of, then you can actually use it further in extending this step by adding its like Taylor series. You have du dt, and then it would even more improve your result. And similar scheme you would have for y, instead of u you would have v component. So this is basically how you find your departure point, and as long as you found that, then you interpolate your phi in that departure point, and that equals to your new value on the grid point with coordinate x ij and y ij, because it just carries to that point. So that's basically how you do it in 2 dimensions, and in 3 dimensions it's very similar. So there are many ways how to do it, how to increase order of interpolation in this case, both in time and space. How to better and better find, how more accurately find your departure point. Because again, I repeat that accurately finding departure point is crucial, because you want to run at high current number with semi-Lagrangian method, because that's the only way it would be more, faster than your Eulerian method. So you need to run at current number much higher than 1. Not much higher, but let's say 2, 3, 4 times maybe higher than, or maybe 5 times than your maximum current number allowed by Eulerian grid. So that's why it's very important to use very high order interpolation techniques, not just first order. Otherwise your solution would be very inaccurate. So that's the essence of semi-Lagrangian method. And so the pros, again, let me repeat, the pros of this method is no nonlinear term. So as a result, there is no nonlinear instability, nothing to worry about. All these kind of issues related to nonlinear interactional waves. So that's pro. And no stability criterion. So there is no like normal in this kind of stability criterion based on velocity field, because you always use interpolation, and you just interpolate, you find thing, there is nothing to get stable, unstable because of this procedure. So large, and as a result, you can use large time steps. Of course, you cannot use very large time step because your velocity field will change and it's going to be not accurate. But again, current number 4, 5 is kind of pretty typical for using semi-Lagrangian schemes. So cons. Lack, or let's say difficult to enforce conservation. So conservation of mass or concentration of transported quantity. Or in case of velocity, conservation of momentum, let's say, or even about energy. I'm not even talking about conserving energy. So that's main disadvantage of semi-Lagrangian. Of course, there are schemes that try to do that, but it's very complex. It's much more complex to do than just using Euler scheme in flux form. So you use Euler scheme in flux form, you automatically get conservation of mass, or maybe not energy. Then you need some extra step, but at least conservation of mass is very easy to, or concentration very easy to enforce, not in semi-Lagrangian. And the reason, because your departure point, it can be some place, and then you just say it's equal to your arrival point. But if you integrate all over the place, it's not automatically, doesn't automatically mean that the mass integral of a whole grid is actually does not change in time. You need to make sure that. There are so-called finite volume methods that basically that can be conservative. So, for example, let's say that you have some grid. I don't know, finite volume one, some arbitrary grid. So basically, what you do for each individual cell, you have these corners. You compute. So those are your arrival points. So you compute your departure points. Let's say here. This came from here, this one maybe from here, and this one also came from here. Yeah. So now this is your cell that was delta t ago. Yeah, something like that. Well, maybe straight lines. So basically, you now say that this cell is completely replaced. The mass in this cell, like for example, mass total integral over this cell, equals to mass over this grid cell. And for this cell, it's going to be not a grid cell, but the important thing for this grid cell, this boundary is going to be the same as, so for neighboring cells, it's going to be like boundary like that maybe. But it's common boundary here between them. So then you just replace values in this grid cells by values in this cells that you need to find by interpolation. So you take, like, you find this piece, from this cell you find this piece, and so on. So you see it's pretty laborious process. So you basically need to compute mass in this departure cells. That's doable, of course, but there is some additional problem associated with that. It's what if your trajectories actually intersect? Your trajectories, semi-Lagrangian trajectories that you compute, they intersect. And in actual real fluid, of course, they don't intersect. And fluid trajectories cannot intersect. Streamlines don't intersect. They don't cross each other. So, let's say that you have these two arrival points, and then you have computing like using one of these methods. You have this departure point here, and for this you have actually departure point here, and you see they intersect. But it's impossible in actual fluid. If you don't enforce mass conservation, other things, maybe that's not really big deal. If in several points that happens. But if you use, like, say, method like that, you would be in big trouble because, well, your cells now flipped in a way, or became very crooked or something. So you need to make sure that your trajectories don't intercept, and that's additional complexity to this problem that you need to overcome with your code. So there are several methods of enforcing that. And then they involve very complicated actually code. Sometimes even to the point that you need to solve elliptic equation, global elliptic, like for the whole your domain elliptic equation for your say some certain parameters, to make sure that your field, that your velocity field, that your trajectories don't intercept, which is additional time, performance time. So basically that's another con, that trajectories can intercept, which can be not desirable feature of semi-Lagrangian method that you use. So overall, semi-Lagrangian methods are very widely used. Like for example, IFS model, the one that used for so-called European model, that gold standard for weather forecasting in state-of-the-art of weather forecasting modeling in the world right now. And that model uses semi-Lagrangian transport, for transporting everything basically in the model. It doesn't use Eulerian grid for transport. I mean Eulerian method for transport. So it's semi-Lagrangian. It's pretty complicated. It's pretty comprehensive semi-Lagrangian scheme that they use. And again, semi-Lagrangian methods always, when you think what to use, semi-Lagrangian method or Eulerian method to treat your advection in your model, you always need to weight. Basically, your main criterion is not so much even accuracy or conservation, but although those are important, but how efficient your semi-Lagrangian method is compared to Eulerian. Eulerian is very efficient because it's relatively simple, relatively few computations you do compared to semi-Lagrangian. But as long as you can run at very high current number, for example, a European model can run, let's say, 5 times or even more faster, using 5 times bigger, larger time step than if it was using Eulerian method. So as long as your semi-Lagrangian scheme is only, say, twice as slow or more expensive computationally than your Eulerian. But remember, in the model, it's not only transport that takes lots of time. It's radiation computation, other things. So in reality, your additional expense for using semi-Lagrangian model can be only, say, 20% higher. Your model would be, the expense of running your model would be only, like, say, 20% higher than with the Eulerian scheme. Then it's usually always, and as a result, you can run at 5 times time step, so 5 times faster your model. Then of course it's worth it. So it's worth to switch to semi-Lagrangian method. But again, it's very difficult to code, to develop into to model, to code. That's why it's pretty complicated stuff, but it's usually worth it. Okay, that's all I had to say about semi-Lagrangian method.